I'm Cyprien Soulaine. So we are going to talk about pore-scale simulation, Navier-Stokes simulation. So the lecture is, I think, a good complement to the open foam class we started 2 days ago. So in this lecture, I'm going to talk about Navier-Stokes, so where it comes from. So we'll derive Navier-Stokes equation, see some properties of this equation, how we can model it with numerical tools, see some simulation example, and if we have time, I will say a few words about multiphase flow. So when we want to model flow and transport in porous media, we can use a cascade of scale nested in each other, and in each different scale that start from the molecular level to the field scale, we can assign a different physics, so different representation of the physics. So at the molecular level, we have statistic mechanics, so we had to deal with the interaction between all the different molecules. At larger scale, the continuum mechanics apply, but we will see that it's not the same law we use whether we work at the pore scale, at the core scale, at Darcy scale, at the field scale. So in the continuum mechanics framework, basically we have two different approaches to model flow and transport in porous media. So one of them, what I call continuum modeling, but here it's not in continuum in the sense continuum mechanics, but really continuum in the sense fluid-solid aggregates. So we have a continuum of fluid and solid. So basically this is here. So all the physics is volume average based on control volume. So in a control volume, you have an aggregate of fluid and solid. We don't know the exact structure of the solid, but instead we have effective properties such as porosity, permeability, effective surface area. In this representation, the flow is governed by Darcy's law. On the other hand, we can have a full representation of the solid structure. So here the solid is completely resolved. And this is what I'm calling direct modeling. We can also say this is a pore-scale modeling. So in this case, the solid structure is explicitly represented. So here you have the solid grain in red, and the fluid, so represented in blue. So very importantly, at that scale, we have an interface between the fluid and the solid. And at this interface, we will need to apply boundary condition. So this is one of the main difference compared with the Darcy scale. And one also of the biggest challenge at the small scale, at the pore scale, to define accurate boundary condition. So we had a PhD student at Stanford who spent his entire PhD to define accurate boundary condition for multiphase flow at the pore scale. So it can be very challenging. What else? So yes, at the pore scale, for the fluid, we use this continuum mechanics law, so namely the Navier-Stokes equation. So just to summarize between the two approaches, at the Darcy scale, so you point somewhere in your domain, you have fluid and solid. At the pore scale, if you point somewhere in the domain, you will have fluid or solid in the grid. So it's never the two at the same time, or an interface between the two of them. Ideally, if your continuum model is accurate, the two different approaches should produce exactly the same results, ideally. So based on this duality, it means that we can solve the flow at the pore scale if your computational domain is large enough, so you solve the flow in the pore scale, you volume average your results, and you can obtain effective properties at the Darcy scale. So for example, you can image a rock sample, you can segment the image into a solid phase and a fluid phase. You can solve the flow. Here, so it's an example of the flow. You volume average the flow, you inverse Darcy's law, and you obtain the permeability. And you can do this kind of thing for all kind of physics. So here it's an experiment we've done in the lab. So it's a microfluidic experiment. So basically, it's a micromodel seeded with microparticles, and the main objective was to visualize the flow. So we see some flow motion of the particle in the domain. And what I really wanted to say with this animation is actually the particle streamlines, the trajectories, they are not random. They are completely deterministic. So which means that if you follow some particle, in average, they will all follow the same pathway for a given pressure drop, always. and they are deterministic, and they obey the continuum mechanics conservation law for fluid. Yes?
Is the trajectory of the particles also deterministic in turbulent conditions?
No. I mean, it's more complicated. When it comes to turbulence, it's more complicated. It can be deterministic in statistic. I mean, you have to average in time for the turbulence. But here we are not talking about turbulence at all. But yes, you have plenty of approaches also for turbulence model. Yeah, so I was saying all this, the flow motion, it obeys the continuum mechanics conservation law for fluid. So these laws, they are derived from mass and momentum balance in a control volume. So here, basically, you have your solid, you have the fluid, and we take a small control volume in the fluid, and we will do this mass and momentum balance in this control volume. So one constraint for the continuum mechanics to be valid, we need to have the mean free path of molecules that is larger than the average size of the control volume. So the mean free path is the average distance a molecule can travel before it hits another molecule. So what it means for us in porous media, it means that if your pore throat here is roughly the same order of magnitude of the mean free path, you cannot use the Navier-Stokes equation. So it's one of the limitations of this model. And practically, it means that when you deal with nanoporous media, like what you have in shale gas, you cannot use this kind of physics. So what we call Navier-Stokes equation, so it depends on people, but I prefer to put S on equation. So for me, Navier-Stokes equation is a set of different equations. So a continuity equation, mass balance, a momentum equation, and boundary condition at the solid surface. So sometimes we just refer to Navier-Stokes for the momentum equation, but I prefer to have the full set of equation. We can also add an energy equation, but we are not going to discuss this energy equation here. So for the mass balance, basically we consider the fluid density, the mass in the control volume, and the variation of mass balance out the mass flux that's coming in and going out the control volume. So this is represented here by this divergence. So I'm using in this lecture the Nabla notation for the spatial derivative. I hope you're familiar with that. And Nabla with a dot, it's the divergence. In fluid mechanics, so this is a classic conservation law for mass. In fluid mechanics, most of the time we assume that our fluid is incompressible, which means that this law can be simplified to the divergence-free velocity equation, this one here. So just divergence of velocity equal to 0, and this is basically the continuity equation we are going to use in most of the Navier-Stokes solvers. So for fluid, it's okay. For liquid, it's okay. When it comes to gas, of course, you will need to use the full continuity equation here. For the momentum equation, so you have the momentum, so the mass multiplied by the velocity, and the conservation of the momentum is obtained from Newton's second law of motion, so which means that the variation of the momentum and the sum of the forces that apply to all the forces that apply to the control volume balance with each other. The forces, they can be divided in two different kinds of forces. So surface forces that apply to the surface of your control volume, and body forces that apply everywhere in the volume. So body forces such as gravity, magnetic, or electric fields. The surface force, so here in red, they are very important, especially at that scale, because they are responsible for the deformation of the control volume. So we work with a fluid, so if you put some markers here in your volume, you will see that with time, actually, this marker, unlike a solid, these markers they will deform with time. So this is what I illustrated here. So we apply, you apply a surface force to your control volume, and you see that the marker will deform. So to quantify the change of the shape and eventually the size of the control volume, we need to find a law to relate to relate this deformation to the physical forces involved. So this is the Cauchy stress tensor. So here this sigma, and we have again two different sources of deformation. One is related to the pressure forces at the on the surface. The second one is due to the viscous stress tensor. So viscous stress tensor can be very complicated for non-Newtonian flow. For Newtonian fluid, like a classic liquid, most of the cases, what we say that the viscous stress is proportional to the rate at which the fluid is being deformed. So this is what we write here, and the coefficient of proportionality is the viscosity. So for Newtonian fluid, the viscosity is constant. If you want to deal with more complex fluid, you will need to have something more complicated for the viscosity. For example, if you deal with blood flow, you will need to have a viscosity that depends also on the strain rate. So it can be very complicated to formulate. So when we combine all these equations together, we obtain this momentum equation, and this is what we call the Navier-Stokes equation. I mean, the momentum Navier-Stokes equation. So we have on the left-hand side the inertia term here, the pressure gradient, the gravity, and the viscous force. What we see actually is that here we have a nonlinear term, very nasty term on v square. This term is very difficult to solve. It's also responsible of the turbulence. And because of this term, I mean, Navier-Stokes equations are difficult even mathematically to prove, so we don't know exactly the unicity, existence, regularity, and there is a $1 million prize if you manage to demonstrate the regularity of these equations. Fortunately for us, in porous media, usually we deal with slow flow rate, and in slow flow it means that the inertia is negligible compared to the viscous force. This term vanishes, and we obtain a simple Stokes flow equation. So here we don't have the nonlinear term due to the inertia.
I have a question. Why do you ignore like the inertial term with the argument that we have flow velocities, but then do not ignore the viscous force where you also have the velocity included?
So, I mean, it's not I ignore. It's so you can non-dimensionalize your equation here. And so the Reynolds number will appear in your equation, and usually for the Reynolds number, the Reynolds number that will come in some slides. So Reynolds number is the weight of the inertia over the viscous force. So it means that if your Reynolds number is smaller than 1, the inertia is negligible. This is what it means. And when the inertia is negligible, it means that you can remove this term from the equations. Okay. Yes. So something important to say also. So most of the numerical tools you can find commercial tool, open source. Soon we will say a few words about that later. They are designed to solve Navier-Stokes equation. So they all solve Navier-Stokes equation. You download OpenFOAM, they solve Navier-Stokes equation. You use ANSYS Fluent, they solve Navier-Stokes equation. But it doesn't mean that if you want to solve Stokes, you need a different solver. You can use the Stokes equation. It's only the term will be negligible. It will not appear in your solution. But you don't need to have something different to solve the Stokes. Stokes is just a degeneration of the Navier-Stokes equations. Okay. So last thing for the modeling part, we need some boundary condition at the interface between the fluid and the solid, so at the solid surface. And this part is very important. So usually what we do, so we need boundary condition for the velocity. So we decompose the velocity in two different parts. One part is a normal component, so the velocity that is normal to the surface, and another one is the velocity that is tangent to the surface. And first, what we can say that the normal component is always 0 because of the mass transfer. So your solid molecules, they cannot penetrate into the solid. Your fluid molecule cannot penetrate into the solid. So this term is always 0. Now the main question is how can you estimate the tangential component of the molecule velocity at the solid surface? So here you have different models. There is no agreement actually in the literature. Most of the time, what we do, we say that in average, the tangential velocity is 0 at the solid surface. If the tangential component is 0, it means that all the velocity is 0 at the solid component, and we call this condition no-slip condition. So in most of the cases, we use the no-slip boundary condition for liquid. For gas, it can be something different. If you cannot make this assumption, you will need you will have your molecules that can slide over the solid surface, and in this case, you will have a slip, and this is the formulation for the slip. And if the slip is really you have a friction at the solid, and then you have a coefficient, the slip length here that characterize this friction at the solid. So it's clearly related to the viscosity of the fluid as well. If it's totally smooth, you have absolutely no friction. It's a full slip, and you have no friction, so just you're sliding without any flow resistance to the solid surface. So the boundary condition can be very tricky, but just to make things simple, most of the time we will use the no-slip boundary condition for single-phase flow. When it comes to two-phase, it can be something completely different. So just to summarize, with some simplification we made, so the Navier-Stokes equations are made of one mass balance equation, divergence-free equation, one momentum balance equation, this guy here, and a no-slip condition at the solid surface. Very important. So when we solve the flow, we are interested in looking at the flow pattern, so the different flow motion of the particles. Yes?
In the case that you have a partial velocity, so there is a component of velocity that will enter in the solid phase. So partial boundary condition.
Here?
Yeah, it's the second case. You have a flow also inside the solid.
No, that's exactly what this condition means. So you have your velocity. So just imagine you are very close to the wall here. Yeah. And your particle, your fluid particles, but it's hard to say fluid particle because we are working in a continuum mechanics framework. But let's say fluid particles. Fluid particles here, so it has a velocity, and we want to find a condition for this velocity. So what we do, we decompose the velocity into the normal component and into the tangential component. The normal component is 0 because if it was not 0, it means that your fluid particle could penetrate into the solid. And we cannot have that because it's a pure solid at the surface. So basically we say the normal component is 0.
But what about the argument that particles can move away from the solid? So maybe it's just a restriction of the sign?
That's what also I'm saying, it's not particles. It's really in the continuum mechanics framework. In reality, you deal with particles, real molecules. So they arrive to the solid and they are reflected because there is a shock and they are refracted. But in average, the velocity is 0. And because when you work in the continuum mechanics framework, you work in average. You don't work with single molecules, but in average volume of molecules. So this is a very important question, and at Darcy scale you don't have boundary condition. I mean, except at the edge of your domain, but because you have an aggregate of fluid and solid, you don't have the boundary condition. But the boundary conditions are included in the Darcy formulation. So basically, in the permeability. You have a constant permeability. It means that the underlying physics has an oscillatory boundary condition. If you have a slip of the molecule, Darcy's law doesn't work actually, and you will need the more complicated laws such as Darcy-Klickenberg or this kind of thing.
Capillary dominated flow, you will still slip?
No, I mean, yeah, it can be, two-phase flow is more complicated. That's why I'm not talking about two-phase flow here. Yeah, so this set of equations are just for single-phase flow. I prefer to talk first about single-phase flow, and we will see two-phase flow at the end. So, about the different flow regimes, so this is some picture you will find in any fluid mechanics textbook. So we've seen this Reynolds number. So the Reynolds number is a dimensionless number that is used to quantify the importance of inertia over the viscous forces. So this is basically something like that, where U0 and L0 are a characteristic velocity and a characteristic length. And what you will find in any textbook, fluid mechanics textbook, is this experiment. So you have a cylinder, and we inject a fluid around the cylinder, and we look at the flow pattern. So if the Reynolds number is very small, when I say very small, it's below 1, so is negligible, you can see that the streamlines follows the shape of the obstacle. And in this case, we use Stokes equation because the inertia is negligible. When the Reynolds number is larger than 1, inertia effects start to impact the flow pattern, and they distort the streamlines. And what you see some recirculation downstream the obstacle here that are generated by the inertia. If you start to increase, to increase the Reynolds number, so when you increase Reynolds number, it means that you increase the flow rate. Then you start to have turbulence effect. So it's completely different topics, and we will need much more than 1 hour to discuss turbulence. So I will not talk at all about turbulence in this lecture. So why I was saying you will find that in most of the fluid mechanics textbook, you have to be very careful about this mental picture you can draw in your mind, saying that Stokes flow means that we don't have recirculation, and inertia means we have recirculation. It doesn't work in porous media. So in porous media, even though you work on a Stokes flow, so a very small flow rate, you can have recirculation. So here I put three examples to illustrate a situation where we are in Stokes flow and we have recirculation. So let's say you have two cylinders that are very close. So two cylinders can be two solid grain. So it's the kind of situation we have in porous media. And here we are in Stokes flow, but we see some recirculation in between the cylinder. Okay. Second configuration, you have the surface of your porous media, and you have a cavity or some roughness. And because of this cavity and roughness, you will also have a recirculation, even though you work in Stokes flow. So when here I'm saying that the streamlines follow the solid obstacles, it only works if you have only one obstacle in middle of infinite domain. In porous media it's different. In Stokes flow you can have some recirculation motion. This will have some importance in terms of mass transfer, because let's say you want to have a chemical reaction at the surface here of your solid, and you will not bring the same amount of acid or whatever because of the recirculation. So it's something you may want to quantify at some point. So, okay. So we've seen that this set of equations, and this set of equations can be complicated to solve. And there is very few analytical solutions actually. So one of them is a solution of Stokes or Navier-Stokes between two parallel plates. So you imagine you have two parallel plates, very large, In this case, we can simplify the problem. The PD is simplified drastically, and we have an analytical solution. And what we obtain this, this parabolic profile. So because of the no-slip boundary condition, we have 0 here. The maximum velocity is in the mid-plane. And it follows this law. If you vertically integrate, vertically average the flow profile, you obtain a relationship between the mean velocity and the pressure gradient. And here what you recognize Darcy's law, where the permeability is h squared over 12. So that will be something important at some point. The other case where you do have an analytical solution is a Poiseuille flow in a tube, in a microtube. So same thing, you have a tube. Because of the invariance and symmetry, you can simplify your Navier-Stokes equation or your Stokes equation. So you have to work in cylindrical coordinate, you solve the PDE, and you obtain again a parabolic profile here. If you integrate, so you volume average the velocity profile, you obtain a relationship between the mean velocity and the pressure gradient. And here, in this case, the permeability is R squared over 8. If you look at the mass flow rate, you will have this law, so the mass flow rate is equal to this law here. So that will be one of the main, this law is one of the main points for the pore network model techniques, if you are familiar with the pore network model techniques. So, okay. So we've seen this equation, we've seen that we can solve the Navier-Stokes equation analytically for a very simple problem, like in parallel, in between two parallel plates and in a microtube. But in reality, what we want to do is to solve the Navier-Stokes equation in much more complex geometry, such as this one. So here it's an image where you have some rice grain and some void. So let's say you go in the lab, you take picture of this image, or you use microcity to have an idea of an image of your pore-scale structure. First thing you do, you segment this image into fluid and solid phases. And then when you have something like that, you want to solve the flow. So here there is two big family of approaches. One of them is to say, okay, I will use pore network. I will approximate the geometry, the pore space, and I will use the pore network modeling technique. The other approach is to say, I will take the exact solid geometry, and I will solve directly a Navier-Stokes equation and a Navier-Stokes problem in this geometry. So let's see first the first option, so pore network modeling. I think you had the lecture on PNM last week, no? So I won't say much, but just to say you have the original image, and what we do first, we approximate the image by a graph of node and bond. And in each bond, we consider it cylindrical bond, and you have this again Poiseuille law that apply in the bond. So with the law we just computed based on the solution in the microtube. On each node, due to the mass conservation, you have the sum of the mass fluxes that is equal to 0, and based on that, you can obtain this law. Then you formulate a matrix, you inverse the matrix, and you obtain the flow in your domain. So main advantage of these techniques is very easy to program. You can have that in a small script, a MATLAB script or Fortran script, whatever. You can compute relatively large domain, up to centimeter, let's say. But of course, you have some drawback also. So you need, the main drawback is you approximate the real geometry. So you do an approximation based on the geometry. And especially you say that the throats are cylindrical, and that can be a big assumption, especially when you deal with a multiphase flow when you have corners and things like that. So you will need to change this kind of flow. My understanding of PNM is that we apply a Darcy scale formalism at the pore scale. So the solution will just give you what you input to the program. And for multiphase flow, there is still a lot of ongoing research that are done on PNM. On the other side, so the direct numerical simulation techniques, here what we want, it's really to solve the flow on the real image. So there is also a lot of different techniques. So one of them is to grid the void space. So you have an Eulerian grid, and you solve Navier-Stokes equation. So we call this family of technique CFD, computational fluid dynamics. So here, because you have the grid, you need to discretize your operator with finite volume method, finite element method, finite difference method. That can be a lot of work to program your own code. Fortunately, we will see also that there is plenty of available CFD software, commercial or open source, that do the work pretty well. So you don't have to start from scratch. You can use something that is already existing. Another technique is called the Lattice Boltzmann method. So it's some technique that is becoming more and more popular. So in this case, we don't solve Navier-Stokes equation, but we solve the Boltzmann equation instead on the lattice. Apparently, it's very easy to program. Same thing, if you look at the Lattice Boltzmann code, it's very short. It can be parallelized very easily, and you don't have this, because we start from the Boltzmann equation, there is no this limitation due to the mean free path and the size of the pore throat. But you also have some problem when it comes to multiphase flow. And another technique is this smooth particle hydrodynamics. So here you don't have to grid the void space. You deal with fluid particles. The fluid is divided by a set of discrete particles. You have to define a kernel to represent the continuous variables. And you track the particle in a Lagrangian framework. So we see that we have plenty of different techniques. So I will say the main advantage of the direct model approach is you deal with the real pore structure geometry, so you don't make any approximation on the pore structure, except that the approximation you do during the segmentation. So here you really solve the physics, so it's not like the PNM where you volume average the physics and you have some law. So here we really solve the physics, but it's much more computational intensive than other techniques like PNM. And for multiphase flow, we still have some work to do, because we start to have good results, but still there is still some work to do, especially for capillary dominated flow. So, as I say, if you want to use this CFD approach, if you start from scratch saying I will write my own code doing the complex grid and discretize my operator and inverse my matrix, maybe you will have your first result in a few years. Probably that's not what you want to do. So there is a lot actually of software, CFD software. Some are commercial, like ANSYS Fluent or StarCCM+. You also have COMSOL. So these two first ones, they use finite volume method. This one use the finite element method. And you have also some open source simulation. So OpenFOAM is becoming more and more popular. It's known to be the open source equivalent of ANSYS Fluent. And it's not only used in research, but it's also used in industry a lot, especially in chemical engineering, automotive, aerodynamics, in airplane industry, and so on. So if you're not following the class and nevertheless you are interested, you can always download the class material to this link here. So few words about the solution algorithm for OpenFOAM. So we see that mainly we have a mass balance equation, divergence-free equation, a momentum equation here, and we have two unknowns, so velocity and pressure. So actually, if you write the thing on the different components, you have four unknowns, so 3 components for the velocity and one for the pressure, and same for the equation. However, when you look at that, you see it's not easy because you don't have any equation for the pressure. So what we need some solution algorithm to solve this pressure velocity couple at the same time. So I will not detail the algorithm, just to mention you, if you use this software we mentioned before, they will most of the time ask you whether you want to use piezo or if you want to use simple. So these are two different solution strategy to solve the pressure velocity coupling. What else? So yes, it's based on the predictor-corrector algorithm. So first we predict a velocity, we guess a velocity, then we solve the pressure equation that has been derived by applying the divergence to this equation. We have a guess of the pressure, then we correct the velocity. Eventually, we iterate around this algorithm to go to the solution. So, what are these two differences if you are in front of this of your computer and the code asks you whether you want to use piezo or simple? So, what should you use? So, first thing you have to know, piezo is for transient, simple is for steady state only. So, if you have a transient problem, you definitely want to use piezo. You don't discuss, you want to use piezo. So if you are multi-phase flow, it means that you are transient, so you want to use piezo. If you want to use a Stokes flow, you see that in Stokes, we remove actually the time derivative. So because we remove the time derivative, it's a steady state problem, so you can use the simple algorithm, and it will converge faster to the solution. So most of the time, when you want to compute just the permeability of a rock sample, you use the simple algorithm because you solve the Stokes equations. So piezo, it's a steady state, but it's not unconditionally stable. It means that you have a restriction, a constraint on your time step. So first thing, you run the simulation, is the simulation crash. It's probably because your time step is too large and you have to reduce it. Okay, so simple is an iterative process, and it's not time step, it's iteration, and we under-relax the pressure field and velocity field. So there is some techniques that combine both the piezo and the simple. So in OpenFOAM, they call it pimple. The main idea is to do transient simulation and with a piezo algorithm. And inside in between two different time steps, they solve a simple algorithm to allow larger time step. That's what is said initially. Yes, also a few things. If you are interested in this algorithm and discretization, I highly recommend this book here. So it's an old book, 1980, by Patenker. So Patenker was the guy who designed the simple algorithm. And here you take few hours, you read, there is 2 chapters, I think chapter 3, chapter 4, and after these 2 hours of reading, you say, okay, I understand finite volume and I have all the basics, so it's really an amazing book, and I really recommend this guy. So, some example. So here it's an image, that was an image of a sandstone we obtained in the lab. We do the segmentation of the image, we take, in this case, only the void space. We put boundary condition at the interface at the surface of the grid here. So no slip. We apply a pressure difference between the inlet and the outlet. We solve the Navier-Stokes. So we grid the pore space. We solve the Stokes flow on a cluster. Here what you see is the pressure gradient, and here what you see is the velocity profile. Then if you want to obtain the permeability, you volume average this velocity profile. Because you know the pressure gradient, you can inverse Darcy's law and you will obtain the permeability coefficient. If you want to have the full tensor, you will need to run 3 different simulations to have the component in each different direction. One thing that is important to mention also, in CFD, so the result can be very sensitive to the grid size. So you have to check if your simulation result will not be changed if you refine the grid. So if it's the case, you have to work with a finer grid. So as a rule of thumb, I will say that at minimum you will need 6 to 10 cells in a pore throat, at minimum. That can be very restrictive at some point. So another example, so one thing we use a lot in the lab is this, what we call the 2D micromodels, and we keep saying it's 2D micromodel, but actually they are not 2D micromodel because it's micromodel, so you have the porous media that is, you have a pattern that is etched and placed in between two parallel plates. So we've seen the two parallel plates earlier. And we keep saying it's 2D micromodel, blah, 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 2D micromodel. But if you want to simulate the flow in this 2D micromodel and you say, OK, I will just take the Navier-Stokes equation and I will solve it in 2D, what does it mean? When you say I'm solving the equation in 2D, it means that you consider an infinitely large thickness. And in your case, this is not what you have because your fluid flow is confined between the two parallel plates. So what you do instead of solving the Navier-Stokes equation, or here I remove the inertia term, so it's just the Stokes equation, you first vertically integrate the Navier-Stokes equation, and it turns out that what you obtain is a Stokes equation plus a drag force, and this drag force is a Darcy term related to the friction of the flow in between the two different parallel plates. So all the unknown we have in this equation, so the P and the velocity, they are vertically average velocity, vertically average pressure. So it's, they don't have any meaning at some location in the thickness, but it's really something vertically average. So you solve this equation, and then you can really compare your result with the experiment, and only then it makes sense to compare the 2D micromodel with the simulation. Okay, so few words about multi-phase flow. So everything I've said so far was for single phase flow. So we have only one phase flowing through the pore space. When it comes to multi-phase flow, let's say two-phase flow, things get complicated. So they get complicated because you had an interface between the two fluids and you have a triple point. Eventually, you have a condition at the interface between one fluid, the second fluid, and the solid. And you have to define the boundary condition here. So the physics is like that. So you have Navier-Stokes equation in each phase. So you have a Navier-Stokes equation applied to the fluid 1, Navier-Stokes equations applied to fluid 2. And you have a continuity of the tangential component for the velocity as a fluid-fluid interface. But you don't have a continuity of stresses. You don't have continuity of stresses because of Laplace law. And Laplace law says that you have a pressure jump because of the curvature of your interface. Okay? So you don't have a continuity of pressure. You really have a pressure jump because of the curvature of your interface. And if you want to simulate this problem, you will need to compute the curvature of your interface and to kind of compute at every time step when you apply the boundary at the interface between the two fluids. So this the Laplace law, so it relates, so here R1 and R2 are the two curvature of your interface, of your surface, and you see the coefficient of proportionality, the surface tension here, sigma, and this surface tension, let's go back, it's really the physical parameters that is responsible of the tendency of the fluid to have less surface. So it retracts the interface, the fluid interface. So at the interface between two fluid and the solid, you can define a contact angle. You can define a contact angle, and that will say whether your solid is wet or not wet, if it's really wet or not so wet, hydrophobic, hydrophilic, something like that. So if your contact angle, so the line you draw between your interface here, so here you have a droplet of water, and here you have air, here you have a flat surface. So you can draw the line here, and you can define an angle. If your angle is larger than 90 degrees, your surface is non-wetting. So you put a droplet, and you will tend to form really a droplet. It will not spread on the surface. If it's 90 degrees, so it will not move. If it's smaller than 90 degrees, your droplet will spread on the surface, and you will have at the end a very thin film on your surface. Based on these different conditions, you will not obtain the same flow pattern. So whether you push a wetting fluid by a non-wetting fluid, or whether you push a reverses a non-wetting fluid by a wetting fluid, you will not obtain the same flow pattern. So in one case, we say we have a drainage. So drainage, let's say you inject air to push water in your pore space, and on the other case, we have what we call an imbibition. So now, in terms of numerics, you have, in this case, plenty of methods. And why we have plenty of methods? It's because it's still a topic of research to have accurate description of multiphase flow, especially when we work in this capillary-dominated regime. So roughly, let's say that you have technique using level set to track the interface. You have other technique using the volume of fluid. Just have to be careful so far. So the state of the art of the simulation says that we cannot go below capillary number at say 10⁻⁵, but truth is probably 10⁻�3. So if the problem you want to solve is really capillary dominated, you have to be careful about the kind of tool you are using and your numerics, because you will have numerical error due to the computation of the curvature of the interface, and because of this numerical error, they can propagate in the domain, and at some point you will have a nice picture, your interface will move, but it will move because of numerical error and not because of the real flow. So you have to be careful of that. The physics of contact line dynamic is still poorly understood, and there is still a lot of work to done, because at some point, let's say you have a very thin film. The thin film can be, say, few nanometers, and you have a pore that was 10 micrometers, so you have a huge separation of scale, and you don't want to have grid cells that are that small, so you will need also to have some upscaling technique to model the thin film. So also one of the other challenge, when you work two-phase flow, you had to work in transient, so you had to march in time. Most of the time we do that explicitly, and you have some time constraint, which means that you have to deal with very small time step. Because you have to deal with very small time step, even though you have the best computational resources, because of the time step restriction, you can have your simulations that will take weeks and weeks and weeks, something like that. So, to conclude, some word about the volume of fluid technique. So this is the technique we use. It's widely used, and this is the one implemented in OpenFOAM. So in the volume of fluid techniques, what we do, we consider a color function, alpha, that is 0 in one phase, 1 on the other phase. At the cells that contain the real interface between the two fluids, we have intermediate value. So based on this color function, we can distribute the value of a single field density. So you have this density we call rho, and in one phase, rho will have the value of rho in the liquid. On the other phase, it will have the value of rho in the gas. If our two-phase flow is a gas-liquid system, and at the interface, we will have a kind of an average. With this single field formulation, we can write a single field momentum equation. So yes, we are working with two-phase flow, but we write only one equation for the momentum, one equation for the conservation of mass, And we also have one equation for the advection of this color function. You can notice that here in this momentum equation, we have an additional term, and this term here is related to the capillary forces. So basically, if you are steady state, it will compute the Laplace law. So everything put together, you have this volume of fluid technique, and this is the kind of simulation you can obtain. So in gray, you have the grain. In red, that was air, and here in blue, it was water. So we did a drainage, and this is the kind of simulation we obtain. So we are doing with two-phase flow. We are dealing with two-phase flow. So you have let's consider we have a flat interface. We have just a flat interface, flat solid interface, a flat solid surface, and you want to displace an interface between a fluid and a gas at this at the solid surface. And let's say that you measure in the lab a contact angle. You measure in the lab a contact angle, but when you measure your contact angle, you measure your contact angle at a steady state. So nothing was moving, it was a steady state. You measure your contact angle, you had one value. So this value actually apply very close to the wall. So let's say at the nanoscale. So which means that if you can grid your geometry up to few nanometers, so you have some grid blocks that are few nanometers, you can apply this contact angle and it will work. And then you solve your flow, and what you, I don't know if, yeah, I can write something. So here you have your interface, you apply your contact angle here, and you will have something that will change, and you will have a bending, a viscous bending that is due to the flow, okay? But still, at the solid surface, the contact angle you measure apply. The thing is, it apply only if you are able to capture all the length scale close to the wall. In reality, this is not something you can do because you will need a very huge grid. And probably the first grid you will have in your mesh will be something like that. So here delta x. So which means that even larger. So which means that you have to upscale actually this information, and the Cox-Voinov is an effective contact angle that include this viscous bending. Yeah. Yeah. So that's why I mean. So the Laplace law is only valid at equilibrium, but when things are moving, you need to have this dynamic formulation, and you recompute the curvature at every time step. Indeed.
In the Stokes flow solution, so you have both the velocity field and the pressure, and then you said you suggest a first solution for the velocity, and from that you get the pressure. But at first steps of the iteration process, you can say, okay, what you suggested as the velocity is incorrect, and then you need to try another guess for the velocity.
Yeah. So in Stokes flow, the truth is the algorithm can be much simpler than for Navier-Stokes, but because we are just using the Navier-Stokes algorithm, I don't design algorithms specific to Stokes because we have algorithm for Navier-Stokes. But you're right, we can do something simpler for Stokes equation.
When the solution converges to some solution,
yeah.
So you tested the velocity field at the first iteration to know that you will get the right conversion because you can get conversion.
Yeah, kind of. I mean, the algorithm is designed to work like that. It's designed to satisfy the continuity equation at every time step, yes.
In this image, it seems you have some like water trapped
So this is a good point. So yeah, this kind of thing can happen. So this is physical, but I'm almost sure that if we want to compare this simulation with an experiment, we will be completely off the reality. And one of the reasons is because of what I said, because of the real law we put at the interface between at the solid surface, so the boundary condition at the solid surface, and the other thing, in this simulation, we have plenty of numerical errors. So that was a nice illustration, but we do have numerical errors, especially in the velocity profile.
As we take many approximations in these things, we're aware of that we're not probably close to the experiment. But my question is, probably we're off in the dynamics, also neglecting inertia. But are we good in estimating the right flow path that we develop? Understand my question?
Yeah. So basically, you want to answer this question. How we can validate the numerical model. So we were very concerned about that, very concerned. And that's why we started to work on PIV, particle image velocimetry, to have very high resolution velocity measurement of the flow. So we had the results in single phase flow much perfectly, and then we use this data to have a high fidelity measurement of the multi-phase flow in the experiment.
You showed these approximations that we made to obtain the Darcy equation, right? But then in granular flow, we usually use that, but then we're also interested in reactions at surfaces or diffusion into stagnant zones and so on. Do you think that's problematic or somehow incompatible that we, even if we're interested in sort of fine scale?
You mean in single phase flow?
Yes, but let's say you have, then if you want to add in granular flow reactions at mineral surfaces and so on. Is that problematic from your point of view?
I will not say it's problematic if you want a chemical reaction. So in chemical reaction, there is two things. There is two things. So first, you have to define a boundary condition for the chemical reaction itself. And eventually, if you have a dissolution or precipitation, you will also have to move the solid boundary in the domain. So that can be a challenge. Then this recirculation, because actually you resolved everything, so that won't be a problem. That will only be a result of your solution. Your problem can be how you will upscale this result to Darcy scale formulation. Yes.
Do you see that upscaling as problematic?
You will have to include this effect. Yes, definitely. I think so.
The last question, please.
In that slide that you were comparing all the approaches at pore-scale, what is the advantage of using CFD over Lattice Boltzmann?
Okay.
More complex?
Yes. It's a difficult question because if I tell you what I really think, and if there is people in the audience that is a big fan of Lattice Boltzmann, you will not like what I will say. To tell the truth, I've been trained with CFD, so I think that's the main reason why I'm using CFD. When you work with Lattice Boltzmann, so let's say when you work with all this approach we call CFD, they are based on this mathematical construction that where you start with mass and momentum balance and you obtain Navier-Stokes equation, we discretize the equation, we solve the equation. So we know all the construction and we know it works well for fluid, liquid, and gas. When you work with the Lattice Boltzmann method, you don't work with Navier-Stokes equation, you work with the Boltzmann equation of statistics, and this equation has been formulated initially only for gas. So there is no proof actually that it converges to Navier-Stokes equation for liquid. And when you go to multi-phase flow, even people who do the Lattice Boltzmann, they say that they have some problem to deal with high density ratio between your two fluids. And the other thing, it's easy to have your Lattice Boltzmann in simple geometry, but when you really want to have a complex solid surface, it's not so simple to implement the boundary condition.